Hi, in this video we analyze in more detail space curves. In particular, we begin to study the notion of curvature of space curves. In a previous video, we studied the concept of curvature of plane curves, together with some of the geometrical information that it provides. The main goal now is to understand precisely what curvature means in the case of space curves, to know how to compute it, and to construct the Frenet frame for a space curve. The study of space curves began with Clairaut in the mid-18th century. Clairaut considered these kind of curves as the intersection of two surfaces. For example, the Viviani's curve is a curve obtained by intersecting a sphere and a cylinder. These are the equation of these two surfaces, and the curve is the red on the image. Clairaut called this type of curves double-curved curves, as he studied the curvature of the two plane curves that result from projecting the curve into two orthogonal planes, as it is shown for the Viviani's curve in the picture. We are going to consider the modern point of view using parameterized curves, in this case taking values in R3. We will define and study its curvature function. For each t, the value kappa of t will measure how sharply the curve bends at that point alpha of t. In the picture, we can see how the curvature is larger if the curve bends sharply, and equals to 0 if the curve looks like a flat straight line. As we did in the case of plane curves, we assume that the curve is arc length parametrized. That is, at each point of the curve, the modulo of the velocity is 1. This gives us a natural unit tangent vector, t equals alpha prime of s. At each point of the trace of the curve, we have a unit tangent vector, and the corresponding tangent lines. We already studied the parameterization of the tangent line at a point of the trace, as that point plus parameter the derivative. Moreover, in the case of space curves, at each point of the trace, we have not only a normal line, but a plane of normal lines, called the normal plane. We now see how much a curve bends at a point in the curve. For that, we analyze the variation of the tangent vector at a point of the curve. The second derivative of the parameterization alpha measures how the tangent vector varies. We call it curvature vector, and we define the curvature as its module. Hence, the function curvature measures how much the curve bends at a point in the curve. The curvature vector is orthogonal to the tangent vector. Indeed, as the curve is parametrized by the arc length, the modulo of the derivative vector is 1. By taking the derivative of the previous equation and by applying the derivative of a product, we obtain that the tangent vector is orthogonal to the curvature vector. Then we can highlight a natural vector among all normal vectors, and this is called the unitary normal vector. This is the second derivative divided by its norm. Taking the expression of the curvature into account, and the definition of the unit normal vector, we obtain the first one of the Frenet equations. We assume that the second derivative doesn't vanish. Therefore, we have highlighted a normal vector at each point of the curve and the line called the principal normal line spanned by it. You can see the parameterization of this normal line on the screen as a point plus parameter a vector. We also have the plane containing the tangent line and the principal normal line at each point of the trace. This plane is called the osculating plane. It contains the direction to which the curve is heading, together with the direction to which the curve is turning. It is spanned by the tangent and the normal vectors. The osculating plane has an important geometric interpretation. It contains the circle that best approaches or approximates the curve at that point. This is the osculating circle. In the image is the green circle passing through P. The center of this circle is called the center of curvature and is given by the expression on the screen. Rho is the radius of curvature, and it's the inverse of the curvature. The osculating circle can be parameterized as you have on the screen. This is the parameterization by the angle θ of the circle in the osculating plane, you can see it in the image, whose center is C of S0 and the radius is ρ of S0. The term osculating comes from the Latin root to kiss because the osculating circle has second-order contact. That is, it has the same tangent and the same normal as the curve at that point P. Before proceeding with the study of space curves, we recall the definition of the cross product of two vectors of R3. That definition is the one you have on the screen for vectors A and B. And we put on the screen also some of its geometric properties. First, the cross product is orthogonal to both A and B. And the direction of the cross product is given by the right-hand rule. Now, using the tangent and the normal vectors defined before, the cross product enables us to consider a new normal vector, called the binormal vector. As the osculating plane is spanned by T and N, their cross product, the binormal vector, is the unit-length normal vector orthogonal to the osculating plane. Hence, we have constructed an orthonormal basis at each point of the trace of the curve. This is the Frenet frame. The corresponding axes are the tangent, the principal, and the binormal lines. The three coordinate planes associated to the Frenet frame are the normal plane, the osculating plane, and the rectifying plane. This last one is the plane spanned by the tangent and the binormal vectors. We finish this video with an example. We consider the parameterized curve you have on the screen. We can easily compute the first derivative, and we check that this curve is parameterized by the arc length. By computing the second derivative, we also check that the curvature function is constant. It is 1 for every value of the parameter. We can also compute the Frenet frame, that is, vectors T, N, and B, and we check that not only the curvature is constant, but in this case also the vector B. Therefore, the osculating plane is the same at each point of the curve. We compute the Cartesian equation of the osculating plane. A point with coordinates x, y, and z is in the osculating plane if it satisfies the equation in the red box at your right-hand side. Taking into account the parameterization of the curve, it is easy to check that the coordinates x and z satisfy the equation of the osculating plane. That is, the trace of the curve is constrained to a plane. In a forthcoming video, we will study how to know when a space curve is constrained to a plane and to know how quickly it breaks apart from the osculating plane. Finally, when the curve is not arc-length parameterized, we have the following formulas for the vectors of the Frenet frame and for the curvature. These formulas are very useful for any regular parameterized curve.